Diaz, and her title is Geometric Model of the Derived Category of Skew-gentle algebras.
Well, thank you very much for the invitation. Well, I'm really sorry that you are going to see again the definition of Skew-gentle algebras, but I think it's important to give it because, well, otherwise sometimes about the definition, right? And I'm really sorry again that you are going to see another model of the same derived category. But I think both of them have advantage. So let's see how this works. So first of all, I want to give the definition of gentle algebras because in some way the skew-gentle algebras can be described using gentle algebras. So a gentle algebra is basically a quiver algebra with certain kinds of properties. They are really nice because in some way we just need to describe the quivers in a really good way. So given a vertex, we have at most 2 arrows ending at that vertex and at most 2 arrows starting at that vertex. And we have certain kinds of relations that help us in some way that given an arrow, there is only one way to go forward and there is only one way to go backwards. So in this case, if we have these kinds of local configurations, that means that we need to add these relations. The second property is that the ideal of these algebras is generated by some paths of length. And the paths that appears in this idea is exactly the ones that we get in the local configurations. And the third property is that these kinds of algebras are finite. An example of these kinds of algebras, well, we have seen a lot of them in this workshop, but anyway, this linear AN quiver is a gentle algebra, but we can have algebras a little bit more complicated than this one. For example, we can have something like this. But then remember that we need to add these extra relations. These ones. And some properties about these algebras are, for example, that is that they are tame. That means that the model category of these kinds of algebras can be defined in a really simple way. And the way that we describe in the composables in this case are in terms of strengths and band models. So basically these things, if you haven't seen before, are words. And in the alphabet of these kinds of words are the arrows and the formal inverse arrows of our quiver. Right. Another property of these kinds of algebras is that actually there exists a geometric model of the model category. And this was given by Karin Bauer and by Raquel Simones. And we know as well that not only that the model category is same, also the derived category is same. This was proven by Drops. And finally, one of the most important properties that I'm going to use in this talk is that exists a geometric model for the derived categories of these kinds of algebras. And this geometric model is given in terms of dissections of surfaces. So basically, what we are need to consider are oriented surfaces. with two different kinds of marker points. A family of arcs. And this family of arcs dissect the surface. Into two different polygons. One of them are those whose edges are edges of the graph, because actually this is a graph. But then that means that we need to have a boundary component without marker points in the interior of the polygons. And the other kinds of polygons that we are gonna get in these dissections are polygons whose exactly one of the arc of the polygon is a boundary component and a boundary segment, and we need to have a marker point in that boundary segment. So these marker points are going to be the vertices of the graph gamma, and these other marker points are going to be the ones that appears in these places. Okay. Why I'm worried about these algebras? Well, basically because there is a really nice construction called skew group algebras, and these kinds of constructions is quite old. And to construct a skew group algebras, we need to consider an algebra lambda. In our case, we are considered over an algebraic closed field. We need to consider a finite group such that the characteristic of the field do not divide the order of the group. And then we can define a skew group algebra in the following way. We need to consider this tensor algebra. And then, well, there is a way to define the multiplication of the elements of these kinds of algebras. So for example, if we consider this group, and we consider this algebra, which is actually a gentle algebra, and we define an action given by this group, and we construct this algebra, what we are going to have is that the skew group algebra is Morita equivalent to the algebra of this shape. So Gas and De La Peña defined a skew-gentle algebra in combinatorial ways, but they proved that actually a skew-gentle algebra is always a skew group algebra of gentle algebras given by this action. So this is going to be a gentle algebra. Okay. So what is again in terms of Peterson relations, there is a way to define a gentle algebra, not using this way. So an algebra lambda or A over I is Skew-gentle. And we basically are going to have the same properties of this gentle algebra, but completely different. So again, given a vertex, we are going to have the same local configuration that before. We are going to have the same relations as before, but we are going to have special vertices and special arrows. And the special vertices appears in exactly 3 different cases. For example, if we have an arrow, a path of length 2 in our quiver, then we can add what we call a special loop, like this one, and we need to consider this non-admissible relation, but it's okay, don't worry. And then this is a Skew-gentle algebra. Or if we have a vertex with exactly 1 arrow ending at that vertex, and that's it, then we can have as well these special loops, or the opposite quiver, like this. So locally, our Skew-gentle algebras look like this. We have these relations plus these ones. So that means that the ideal is generated by some paths length 2. And these non-admissible relations, 1 for each special loop. Again, in this case, what we have is that the algebra is finite dimensional. Okay, so I'm going to show you an example that actually you show us as well, which is a DM algebra. I don't know if it's not that. Sorry, this is another one. So, using a similar game that I used in that part of the board, we can prove that this algebra, well, it's not the same game. I'm sorry. Using a different game, we can prove that this algebra is isomorphic to this one. With the commutative relation. And I'm pretty sure that most of you know exactly what kinds of algebra is this one, because it appears in cluster algebras so many times. And this algebra is coming from a particular ideal triangulations of surfaces. In fact, it's actually from the following triangulation. So if we compute the quiver of this ideal triangulation, if we compute the potential of this ideal triangulation, what we're going to have is exactly these quivers and these relations. So in some way, Skew-gentle algebras appears in these kinds of triangulations, and actually this example is more general. If we have surface with marked points and punctures.
Are you missing an arc there to the puncture?
Yes, there's a puncture.
But don't you want an arc to the puncture also?
Yeah. Sorry. So again, if we consider oriented surfaces but with punctures and with boundaries, exists always a triangulation T. is that if we consider the Jacobian algebra given by the quiver of that triangulation and that potential, this is going to be a Skew-gentle algebra. And this observation is super important because help us to prove a lot of things. Okay. So some remarks about the Skew-gentle algebras. In the similar way as we have some properties of the gentle algebras, we also know that the algebras are tame. We have as well these kinds of things, strings and bands. We also have a geometric models of the model category. And what we want to prove today is that we have as well a geometric model of these kinds of algebras. Something that I really would like to write down is that this derived category stain. This was proven by Beckett, Marcos, and Merkel. And the way they did this is they use Plusius as well, but they define rewrite these kinds of combinatorial objects in terms of homotopy strings and bands. Basically, these kinds of things are words, but now the words, the alphabet of the words are paths in the quiver and the formal inverse. And we need an extra data, which is a grading. And this grading is basically, well, it's telling us how to write the complex, but that's it. It's nothing more than that. So this grading is basically a sequences of integers. Okay. So now, the profile model. And the theorem is also that it was proven as well by Teremiot. And we proved that we can describe or we can give a bijection between Skew-gentle algebras if we exclude exactly 3 algebras, otherwise this is not a bijection. This bijection is between the Skew-gentle algebras and what we call orbifolddissection. And as in the gentle case, we're going to have a similar definition. So we are going to have as well, in this case, an oriented surfaces, but with orbitals of order 2. So we are going to have 3 different kinds of points, M, N, our orbitals of order 2, we are going to have a graph. This graph is also is going to dissect as well the surface into polygons, but in this case, gamma S into that kinds of polygons and what we call degenerate polygons, the ones that has orbifolds in the interior. I'm going to include the other ones, not just that I don't want to draw it again. But we have these ones and the ones that we have in the general case. Okay, the way that we prove this is quite simple. Basically, what we do is we consider a Skew-gentle algebra. And if we delete these special vertices, what where we're going to have is always a gentle algebra. And we know how to construct, how to get a really beautiful geometric model for these kinds of algebras, right? So what we do is to construct the geometric model for this gentle algebra. And then we need to recall that we have a special vertices. And what we do is to replace those arcs that corresponds to the special vertices by these new arcs ending at the orbifold vertex. Okay, so an example, these kinds of things is the following. In this case, the surface is quite simple, it's a disk. And if we want to draw the quiver, what we have to do is the usual thing. We are going to have a vertex for each arc. We are going to draw an arrow between two arcs if they have like if they share an edge and they are in a good position, like this. And what about the relations? Well, if two arcs are in the different polygons, then we are going to have a relation. So in this case, these two arcs are in a relations. These two arcs are in a relation. However, these two are not in a relation because they are in the same polygon. And remember that we have these special arcs that ends in an orbifold point. Then we need to add these special loops. And if we remember, whenever we have a special loop, we need to add as well a relation in this case. So that means that our quiver is the following. But I have to trace. We know more about these kinds of models. We know that actually, if we consider, this is the first part of the term, the second part of the term is that if we consider certain kinds of arcs, gamma, with a gradient, which is this gradient is exactly the one that we have in Berket, Marcus, and Merkel theorem. Then we don't have a bijection, but we induce in the composable objects in the derived categories of these algebras. And what kinds of arcs are the ones that we need to consider in this case? Well, we need to consider arcs that start and end in these yellow points. Like this. Or things that start in a yellow point, but then goes around a puncture like this one infinite times. Or these kinds of things. Or closed curves. But in this case, we need to be careful because, first of all, we need to consider up to homotopy classes, up to orbi-homotopy. And also, we need to consider in this case that the gradient, which is really reading the wiping number of the curve, is 0. So yeah. So even if we don't know, if we don't have a bijection between curves and in the composables, we know when these arcs induce in the composables, and we know when these arcs induce some of the decomposables, and we know which decomposables are the one that appears. So, for example, let me, well, I'm gonna draw an example in this. Dissection. So in this case, whenever our curve is symmetric, we know that the context that we are going to have is in the composable. But if our arc is not symmetric, like in this case, then our complex is going to be in the composable. So in this case, the way that we constructed the complex is super simple. We basically have to follow the curve super carefully. So the first point that we find is this 3. So we need to consider the projective in 3. Then we follow the curve super carefully, and we arrive to this place. But then this curve is opposite to this arrow, and this arrow is, let's say, A. So we need to define a map between this projective. Then if we follow the curve, we arrive to this special edge. So we need to continue because it's direct. But then in this case, we arrive to these particular vertices. And remember that these vertices corresponds to 2 decomposables in the adhesive representation, like in the example on the right. So that means that in this case, we're going to have B2 plus B2 minus. So we're going to have the sum of the 2 projectives. And then if we follow the curve, we are going back to B. So that means that we need to draw something like this. And there's a really easy way to define these maps between these 2 projectives, again, following the results of Merton and Merton. Okay, so to finish, I can take 1 more minute. The third part of the theorem is that whenever we have an intersection, a crossing, and the grading coincides, which is important, otherwise there is no a map between these curves. So in some way, if the crossing is good, then we can describe a map. If this is gamma and this is delta, from P gamma, P delta, and to P delta to the shift of P gamma. This is the case when the intersection is in the interior. If the intersection is not in the interior, then we are going to have only one map. The proof of this result is quite simple, and what we use is basically the geometric interpretation of that Morita equivalent property that Claire and Boostley did. And what we do basically is lift the curves. We are going to have a crossing in the gentle case. In the gentle case, we know that we have maps, and then we need to apply the functor. And what we get after that is that we are going to have a map in the gentle algebra, in the Skew-gentle algebra. However, that proof is not giving you exactly the maps that you have between these two complexes, but what we did is to describe them explicitly given the complexes.
You, are there any questions?
So in your part 2 of your theorem, if there's only an arrow forward, it says induce, but is this a bijection?
This is not a bijection, but it's only induce. So the problem is that some of these arcs, which are symmetric, so when I'm saying symmetric in some ways that you go right to an orbifold point and right in the same way, then these kinds of curves induce two indecomposables objects. And if you're working with cross curves, sometimes you get two indecomposables and sometimes you get four.
But that's the only problem.
That's the only part.
So you get a geometric model, you get a bijection with the indecomposable objects. And do you get information about the morphisms between them, or the algebra?
We have a description of the maps given by crossings, but the problem with the Aslander right and quiver is that there is some parts that are not working well yet. So that's something that we would like to solve.
Okay.
Soon.
Okay. But there's some hope.
Yeah.
Great, thank you.
So the nice thing about gentle algebras, right, is this work that's been going on is that the surface and the topological information of the surface encodes the derived equivalence class. The slightly unsatisfactory thing about Skew-gentle algebras is they're not closed on the derived equivalence. So is it true? Do you think that there's a way of describing a closure about class and the derived equivalence using the surfaces?
Yes, it is actually Claire and Thomas prove that there is a way to decide whether two algebras are derived equivalent.
But that's Skew-gentle algebras. But what about, you can leave the class of Skew-gentle algebras.
That's the problem.
But are those algebras still visible on the surface, or coming from the surface? Is there a way to describe the algebras which are derived equivalent to Skew-gentle algebras using the function surfaces?
That's a good question, but I don't know if there's a way to do it.
The equivalent question is whether you can describe collections of arcs that give tilting complexes. And if you can describe the maps, then that feels like it should be achievable, but
Okay, maybe
it's not.
maybe it's possible then, because if we use the work of Claire and Thomas, they know how to find tilting objects. Yes, we can find the rest.
I have a question. Sometimes there's more than just a one-dimensional space of maps between two projectors. I believe. So, like here, you have a map from P1 to P2, and you say it's F of C. But if there's several possibilities, does your surface tell you which one you have to take?
Unfortunately, no. I mean, you really need to go to the stream and decide there which maps you have here.
But you can do it.
You can do it. Yeah.
Mhm.
Using the work of Beckett method is possible. But not from the surface, but because in the surface you lose that information in some way.
Don't see any other questions, so maybe we can thank Yadira again.